Swayam Prabha. Digital India. Educated India.
Okay, so let's get on with the second lecture. So I think what we decided to now look at was fluid flow, right? And how do we look at it? Okay, so as I think I discussed a little bit in the last class, so there are two ways of looking at that, right? So there is this Lagrangian view, right? And there is the Eulerian view. Okay. So why do we even need to sort of look at fluid flow in different perspectives, or what is this and why are we even discussing this? Hopefully slowly these things will start making sense. Okay, so what exactly are we saying when we talk about, say, Eulerian? Let's just get some descriptions out of the way and then we'll try and discuss and understand. Okay, so Eulerian, essentially what do we do, right? So now what is it that we are trying to understand here, and why am I looking at different ways of looking at how a fluid will flow, right? So what I'm basically trying to understand is that when a fluid, right, will move, when a fluid is moving, it has a certain velocity, right, and it is moving from one position to another, one physical position to another, right? What effect does that have, right, on its physical properties? Now this is different from a solid. I mean, you can take a solid ball and you just throw it, its mass doesn't change, you give it a certain velocity, you can throw it at a certain momentum, it will move in a certain direction, but its density is not going to change, right? But fluid is different. We know fluid is different, and that's why we have control volumes, and that's why we spoke about fluid as a continuum, right? So in that context, so we need to understand how we are looking at fluid flowing, right? Because I also need to know if fluid is moving, right? So say I have this huge ocean, right? So what is the density, for example, of the water, of the ocean water? Is it the same everywhere? So because at one point of time, if I was looking at a particular location, that location is changing after some time. I mean, the fluid particles which were there at that location, notice I use the word particles, right? And we explained that in the last, we discussed this in the last class, where particles were a little different from molecules. So if I were to, if the fluid is moving from one point to the other, there are different particles of fluid right now, at a particular location which I was focusing my attention. So what happens? Does the density change? Does the velocity change? How does it change? Velocity. And how do I calculate velocity, by the way? Do I calculate velocity of each particle? Or how do I say velocity of fluid? What do I mean by that? Compare that to as if, taking, say, for example, a cricket ball, and the velocity of that ball, right? So this is a sort of, I won't say complication, but this is how fluid mechanics, fluid dynamics becomes very interesting, right? So in that background, we're basically looking at this Lagrangian view and an Eulerian view. Okay, let's get down to very basics and looking at some very basic descriptions, and hopefully it'll start making sense. Okay. So Eulerian, so therefore I'm trying to understand the physical properties of a fluid which is actually flowing, right? So Eulerian is I actually calculate the pressure, of the flow. So here what I'm actually doing is we compute okay, is that good enough? Okay, let's do that. All right, okay, no problem. So we are looking at Eulerian, right. So, what we do here is we compute the pressure, right, of the flow. Okay, and pressure, which is essentially a function of the space and instant of time, right. So, we compute the pressure of the flow. You understand what we're trying to do here. So, if I have a flow, I fix my attention at a particular location, which is x, y, z, right, at an instant of time t, right, and I calculate the pressure at that point, right, and we will probably calculate other properties from this pressure description. Okay. So, we will come to that later on. So, now the other one, which is the Lagrangian, right, which is the Lagrangian. What we do here is we follow individual particles through the flow. Okay. So, of course, the spelling of through is wrong, but okay. So, so we follow the individual particles through the flow, right? So, that is essentially Lagrangian. So, let me try, let us try and understand what I am talking about. So, let us take an example, right. Now, for example, now I have a classroom, right. I have a classroom. This is the door, okay. This is the door of the classroom. Okay, right, and okay. So, you have people coming into this is essentially my classroom, the space here. So, these are the say the bench, the seating for the students. This is the seatings for the students, say. Okay, let us just say that that's what it is. Okay. So, now you have students coming in. Okay. So, you have students coming in here. So, constantly, so you will have students here. Okay. Okay. So, something. Okay. So, you have students coming in into the classroom, right. Now, for me, say I am standing right here, right. This is myself, right. So, let us just say that I am standing right here. Okay. Now, how am I going to observe? I mean, what you will be like, okay, so you are standing here, students are entering the classroom. So, what is it that you want me to see? And if I say see differently, what does that even mean, right? So, let me see if we can just view this scenario in more than one ways, right. So, I have a classroom, there is a person who is standing at say location A, who is standing at say location A, okay. Right, and I am trying to view the scene happening in the classroom, right, where students are essentially entering the classroom, and I am saying that there could be more than one ways of watching it. Okay. Now, let us do this. Okay. Let us fix our position, okay, and let that be the door. Okay. Let this be the door. So, I am going to call this location as say B. If this is the location B, right, and my door is my the focus, right, what I am going to basically look at is how the number of students entering this door is changing at every instant of time, right. That is what I am going to look at. That is what is happening near the door. So, at every instant of time, how many students are basically passing through it, right, passing through the door. Maybe some people are stopping for a little while and then moving on. So, what could be possibly the change of velocity, if I may, at near the door, right, and whether there are some taller students, whether there are some shorter students. So, whatever physical property you want to look at, okay, what kind of students, are they from different countries, whatever, right. What is another way of looking at this? So, I am basically focusing my attention on the door, and I am looking at all the physical changes possible, right, in the students who are entering the door. Maybe even a few are even trying to leave, right. Okay, so that is one way. The other is, what could be the other way? So, what the other thing is that I focus my attention on a particular student. Let us say I am going to look at the student whom I have marked in red, right. Then this student enters at a certain time, right, I count that, right, and then this student sort of walks around, does this, goes here, talks to somebody, walks up, goes here, talks to somebody, no, then he comes here, talks to somebody, again comes back, and then sits here. So, let us just say that this was his initial position, which was say A, and now this is his final position, which is say B. So, this is another way of looking at it, where I focus my attention on a particular student, right, who is entering this classroom, right, and he moves from position A to position B, right. So, if now sort of give us a little more of our fluid mechanics feel. So, therefore, if I am looking at say a fluid moving, right. So, I would be looking at a particular location, which let us say this B is say x, y, z at an instant of time, right, and at every instant of time at this location I will look at the changes in pressure. Else what I will do is I will focus on a particle of fluid. So, essentially I am going to look at a particle of fluid like that, right, or if I were to draw this, I could essentially a 3D, this is nothing but a particle of fluid. So, I am going to look at particle of fluid, right, and that shall, and we will follow each of those particle of fluid and follow it, till however much you want, till whatever time you want. So, I am going to follow the path of this particular particle and compute the changes in the physical properties. So, that is essentially a brief idea of what exactly Lagrangian and Eulerian we are talking about. Okay. Now, another way of looking at this whole thing, because I am now trying to think how we are going to bring math into the whole thing, right, because that is where we have to get to. So, for example, if you see we compute the pressure, right, pressure change, right. So, pressure change, so but I am going to look at like if I take a control volume for that matter. So, if I am going to look at this here, right. So, I take a certain mass of that fluid and compute the change of the flow, right. So, I will take a control volume and then compute the changes in the pressure, right. Lagrangian on the other hand, so I will probably take I am talking about particles here. So, that means I am going to take so of course, this is my domain, this is my complete domain, but I am following one small particle, which means that I am discretizing. I am discretizing it, right. I am discretizing my view, which essentially here is I am looking at the flow here in a very discretized form, right. I am looking at this particle separately, I am looking at the other particles separately, I am following them separately, and I am looking at them, each of them, right. So, I am actually looking at a discretized form of this fluid, right, where again it is still a continuum though, and that is how I look at the change in properties, right. So, this essentially should tell you that how the math is going to turn up, right. So, if I want to talk about that. So, let us sort of, so again, so yeah, okay. So, I think that is the example I wanted to give. Let us see now if we can put some math into it and see if all of this makes sense. Okay. Okay, so now let's just say we look at a velocity field. Okay, this is the sort of an easiest thing to start. Okay, velocity, because we're talking about a fluid moving, right? So we're looking at a velocity field. Okay, a velocity field. So how do I define that? I'm going to define that as v, right, which is a function of space and time, right? Space and time, this is a total velocity, and it has three components. It has its three components, which is u, which is also a function of space and time. Okay. Which is again a function of space and time. So essentially v has three components, right? U, v and w in the, so I'm looking at essentially right, origin of coordinates. So I have a 3-axis, right, 3D general flow, and my velocity field is essentially this. So I have a u, okay. Okay, so I have a u, I have a v, and I have a w. Okay. Okay, so that's what I am essentially. So that's the velocity field, right? So now let us calculate. How will I calculate the acceleration of this? Right? How will I calculate the acceleration of it? So let's say to take it simply, acceleration. Okay, I'm going to do that. So now acceleration, yeah, write it as a or f, right, is what? What is acceleration? I think I don't need to explain that. Okay, if this is fine, now let us go ahead and discretize the velocity in here, right, as we have it. How would we go about doing this? So here it is a function of 4 components, right, so rather 4 variables, right, x, y, z and t, right. It's a function of space and time. So therefore, what sort of derivatives are we going to take? Okay, partial derivatives. Okay. Now I think this is also a good time for you to, I'm going to explain a few things once you get to the material derivative, that is. But I think this is also the right time to sort of remind yourselves, the type of from your calculus studies earlier on, that what do we understand by, for example, partials, or say something like that, right? Or this, what you're going to learn today is, if you already don't know about it, is something like this. So this is the kind of derivatives that we are usually we will use, right? So I think it's time that you remind yourselves what we're talking about here. Okay, so we have multiple variables, so therefore the primary properties is going to change with respect to each of them, so therefore we're going to use partial derivatives. Okay, so how do I do that? So essentially what I say is this amounts to the change with respect to time, right, change with respect to time. Okay, okay, change with respect to time, then okay, I can write this, or let me sort of try and if I do this, okay, or let me sort of try and derive this for you, right? Isn't that a good thing to do? Should I? Okay, let me just give me a second. Should I or should I not? Okay, no, continue this. Okay. So then the other thing is, so now I take this, then I do this, it changes with x, right? Is that okay? Right. So my derivative is with respect to time here, right? So then respect to time. Now these things are also changing with x, y and z. So how do I do that? So del v, del x and del x del t, right, plus del v, del y this, right. So now if you know, so if that is the case, what is del x by del t? What is del x by del t? So this is nothing but u del y del t is nothing but v del z del t is equal to w, right. Is that fine? Okay. So we do that. So then let me again write this down. So therefore the acceleration becomes, so then this becomes del v del t plus u del v del x plus v del v del y plus w del v del z, right. So I think now that you can see that the first term here, right. So the first term here is essentially telling us the change in the velocity at an instant of time, you know, it's localized. So you could think of this as, you know, looking at the door and how things are changing there, where the velocity, you know, you could take the velocity is changing every, say, minute, you know, it's delta t. So I mean, how big or small is your time interval is up to you. So you could do that. So that is essentially the kind of thing we're talking about here. So this is essentially what I say as local acceleration. This is my local acceleration, and the other one, which is this bit, right. So this is basically the change which is happening because of movement through the fluid. So it's actually the fluid, so actually it's moving from one point to the other, right. So therefore this is how it is different from a fluid, if you can see. So if you would like to sort of compare this to how you would do it for like a solid body, I think it will start making sense, right. So here the second part is essentially the convective acceleration. So convective acceleration is essentially because it's moving physically, right, from one point to the other. Okay. Now here, okay, so now let us use a gradient operator here. Okay, I'm going to just stick to this. Okay, now if I use, say, a gradient operator which looks like this, right. So okay, so this is the gradient operator. Okay, my hats are not very good. Okay, so this is my gradient operator. Now, if I use this, can I write the acceleration using this gradient operator in a certain way? Right? I mean, I'm trying to see if I can write the convective acceleration in a certain way. Okay. Now, just think about this. So let's just say. Okay. Now, let us see what this means. V dot del into v, right. So, which means this, right. Now, v is what? V is u right, and your del is okay. So, this is what it is. So, if I take the dot product of v dot del, what do I get? If I do v dot del, so v dot del is equal to u del del x, right, plus v del del y plus w del del z, right. This is kind of another operator. So, then v dot del is equal to, so if you see this, right, so this is nothing but u del v del x plus v del v del y plus w del v del z. Does that make sense? Okay. So, essentially we are just multiplying the whole thing by v. This is the vector v, right. So, this is what we get, and if we go back to the previous thing, what did we get here? So, this is what we had got in the earlier case, u, the convective acceleration. So, now if I come here, so I get the same thing, right. So, therefore, in the sense that I can essentially write, right, I can essentially write the acceleration. So, the acceleration can essentially be written as del v del t, this is the local, plus right v. Right. So, I can write it in this fashion, and you should know that this actually means, this is essentially nothing but the convective acceleration, right. This is essentially the convective acceleration, right. And so, then therefore, I can sort of write this down. So, what is so interesting, or is there anything specific that you notice about these terms? Because ultimately, when I have terms like these, and these are going to be in equations, I'm talking about accelerations, I'm talking about velocity. So, these are going to be in equations. So, what is it that, why am I looking at this a little more in detail, right? See, this is, if you see here, I am taking a velocity component and multiplying it by a derivative of another velocity, right. So, these terms, the convective acceleration terms total, that convective acceleration is actually nonlinear. It's a set of nonlinear terms, right. Now, this is going to bring complexity into your computational calculations when you draw up equations and stuff. So, that's where the challenge is going to come from, right. So, when I do something like this, physically I think it's not very difficult to understand. I think we are understanding that, but slowly the picture is emerging where this is going to be, this is a nonlinear term. So, therefore, solving it is going to be not very trivial. Okay. So, that's what essentially thing. Okay. So, so if I were to therefore now sort of ask you, so again, so going back to Lagrangian to the Eulerian. So, the Eulerian is essentially, I am looking at in the total change, right. I am looking at the total change. So, if I look at that, so this is essentially your, in the Eulerian system, right, if the if you are looking at the change. So, essentially this is the total change. So, this is the instantaneous change, or the local change, and the convective change. So, this is essentially the if you were to look at the if you calculate the acceleration in this fashion of the given velocity field, you are essentially taking an Eulerian view at it, right, in the Eulerian system or Eulerian view. Okay. So, that is exactly what it is. Okay. Now, this del operator is very interesting. I will say two things about it at this point, and you know, it's very interesting. So, when you use this del operator, okay, so in this fashion, when you use this, you are basically generating the convective acceleration. Now, what if? So, I wrote this down here, right. So, for example, now I have, say, so now if you see here, I took the dot product of the velocity vector and the first the velocity vector and then the operator, right, v dot this thing. What if I did this? Okay, so what if I did this? What would I get? Right. So, what would I get? So, it will be del u del x plus del v del y plus del w del c. Okay. Okay. Now, if this is equal to 0, then it means the flow that we have is essentially we should find if the flow is essentially incompressible, and this is you know, some basic understanding of fluid mechanics which you should be able to find in any standard textbook. Okay. So, I advise you to sort of go through that, because doing the details of this now is not going to be in purview of this class. Okay. But it will be interesting for you to, you know, so what exactly does this mean, incompressible, right. So, del dot v is equal to this. If so, if I say incompressible fluid, so you should immediately say, oh, so del dot v, the velocity field, is going to be 0. Okay. And of course, what if I did this, right? I could do this as well. Now, this and I could, you know, write it out, right, I j k and the components, etc., etc. If I did, and if this turned out to be 0, right, then I guess this, you know, this is going to be irrotational. So, physically essentially means that it's going to be irrotational if it delta cross v is equal to 0. Okay. Right. Now that we were talking, now we have been talking about, you know, derivatives. Like I said, you know, please you know, get a hang of it. So, fine, I am going to do something here now before we, you know, close this class today. So, so this is some usefulness or some of the ways that the del operator is going to give you an idea of the physical nature of the fluid that we are dealing with. Okay. Now, see, it's a fluid flow, right? It's a fluid flow. Flow also can happen in more than one ways, right? It could be incompressible, it could be irrotational. There is flow, but it is flowing in a certain way where it is irrotational. What does that mean? Right. So, it basically means the particle that you have, the particle of fluid, it is moving, but it is translating, but it is not rotating about its axis. So, that is when it becomes irrotational. Now, how do I put this down in terms of math, right? So, if I have to tell my computer code that is what is happening, how do I do that? So, what I do that, the way to do that is saying that the vector product, right, the cross product of the operator and the velocity vector of the flow field is going to be 0, right, that, and it is incompressible, right, which is the dot product of the operator and the velocity is going to be 0. Okay. And if I have an Eulerian field of view, then this sort of this here is essentially giving me the convective term, right, of the change in the fluid. Okay. All right. So, now There is something, there is a something called the total derivative of material derivative, right. So, let us just understand what that is. Okay. So, what I am going to talk about is what exactly is a material derivative, right, or total derivative. Right, and this is something you write like this. For a fluid, it could be anything. It could be density, temperature, viscosity, whatever it is, velocity, of course. So, it could be anything. So, this is the material derivative or total derivative. So, it's essentially you are looking at a change in the properties, a change in the property with respect to time, right. Okay. So, now let us have a so, I have this axis system here, right, y, right, and let us say we have a fluid particle, right. Let us say we have a fluid particle. Okay. So, at say time t, t1, okay. So, at say time t1, okay, this location is essentially say x1, y1, z1. So, this is the position essentially of the particle, right, and also the velocity say is like this, say it is 1, okay, because let me just, so this is the location 1, right, this is location 1, its position is x1 z1 y1 z1, it is at time t1, it is velocity is v1. Now, if the velocity is v1, the velocity what I have shown here is a vector, right. So, the direction is also important. So, I could do this differently also, right. So, this is essentially it looks like it is going in the x direction. So, that is the only velocity component it seems to have, okay. But it does not have to be that way. So, I am just drawing it here. Okay. Now, so this particle, okay, has these properties that is located at 1 at the location 1, right. So, let us now take the same particle and where it is at say time t2. So, let us just say it is here. Okay. Okay. So, the particle is here, okay, and this is the location which is this, okay. This is what it is, and therefore, and this location is x2, y2, z2, and it is this is at time t2, okay, and let us just say that the velocity is something like this, okay. So, this is nothing but v2. Okay. Now, what I will do is I will trace out its path. Okay. I am going to trace out the path. So, I am going to just say that this something like that. Okay. So, it moved from say position. So, let us just say okay. Okay. So, it moved from say position 1 to position 2 and this is it, right. So, right. So, I am not writing this down again. So, you can see what is going on, right. This is the stuff. Now, so this is you can see that I have a 3D picture over here, right. I have a 3D picture over here. So, let me just track the change of the velocity, say in the x direction, right. It is moving, you can clearly see that there are changes happening in x, y, z, it's moving in all the three things, etc. Okay. So, if I do that, so let us just say that I am looking at, okay, yeah, so I am looking at, say, okay, this is my v, right, and I am looking at this in x direction, right. I am looking at in x direction. So, say, so here it going from x1 to x2, right. So, then it goes from, these are the two locations, this is x1 to x2. Okay. So, if that is the case, so here okay, okay. So, let us just say that okay, at x1 this is v1, right, this is v1, right, and at x2 it is v2, right. So, this is, it is changing from here to here. So, essentially what I am looking at here is, if you look at this, right. So, if you look at this, so I am going to call this as, say, theta, I am going to just call it that. So, therefore, this, can I say that this is v2 minus v1, can I say that, right. So, this is essentially nothing but the change in the velocity, right. I am taking the linear change in the velocity, and this location is this, and this one is the position change, which is delta x, which is equal to x2 minus x1, right. So, then tan theta is equal to delta v by delta x, which is equal to v2 minus v1 by x2 minus x1, right, x2 minus x1, right, is that right? Okay. Now, or can I just write it like this, right. So, if I were to write it like this, delta v, okay, is equal to v2 minus v1 by x2 minus x1 into delta x, right, delta x. Yeah. Now, using the definitions of derivative, right, which is that this term, right, I can write this term as a derivative in what way? We can write this provided that this x1 and x2 are very close to each other, right. So, in the sense I can write this, right, this term, right, I can write this as, if I can write this as limit is this, right, or x2 minus x1 sort of tends to 0, then I can then v2 minus v1, x2 minus x1, then this can be written as del v del x. This is by definition, right, this is by definition. So, therefore, what I am saying is, therefore, I can write this as, right. So, del v, so I kind of missed the somewhere down the line. Okay. So, I think I should have the arrows here everywhere, please bear with me. Okay. So, here also and here also, so here also, right. So, therefore, what we can say is that, let us go to the next page. So, we can write this as, so delta v, so therefore, we can basically say delta v is equal to del v del x, right. Let's go here into delta x, okay, right, into delta x. So, similarly, I can do the same thing for y and z directions as well, of course. So, then what do I get? So, then I will get this is equal to del v del y into delta y, del is equal to del z into this, and of course, del v is equal to into delta t, right. So, therefore, these are the total changes in the velocity, right. Let us just go back a little bit. So, essentially we are saying it moves from point 1 to point 2, and this is what we are looking at. The this is a particle fluid is moving from location 1 to location 2, right. We are following that particle. Then what is the change in velocity? Change in velocity is happening with respect to time as well as the location, right. Velocity is changing because the location is also changing. So, and so what we did is we took each of these the axis, and we found out the change in the velocity, like in the 3 directions, right, and also in time. And so, that if I write it down, so this is basically the change in velocity in the x direction. So, it is change in velocity in the x direction, y direction, z direction, and the change in time, right. So, if this is it, so then therefore, what is the total change? So, the total change therefore is the total sum of this, right, total sum of this. So, therefore, I can write out, so this is the total change, which is del v del t into delta t plus del v del x into delta x plus del v del y to delta y plus del v del z this. So, we will do some little bit of math now, divide by delta t throughout. Okay. So, therefore, this by delta t is equal to del v del t plus del v del x by delta t del v del c del z, sorry, okay, is delta t. Then of course, you take limits, right. So, we will take the limits such that limit delta t tends to 0, right. If that is a limit that I will take, right, if I do that, so then everywhere, so then here also you take a limit, right. So, throughout, so limit delta t tends to 0. You take that for this whole thing. So, you take limit delta t tends to 0, you take limit delta t tends to 0, right. So, now you know what we will get there. So, del x by del t is essentially the velocity, right. So, therefore, what we get now, okay. So, therefore, so this is the acceleration. This is the acceleration as delta t changes to 0, but this is an acceleration. So, let us just write acceleration for the time being. Okay. So, then this becomes del v del t plus u del v del x plus v del y plus w del v del c. So, you have a convective part and you have an instantaneous part. So, therefore, this is the, as I said, I summed up all the different velocities. So, therefore, this is what is essentially denoted as dv dt. This is your total derivative. So, this is the basically the total, right, or material material change in velocity, okay, material change in this case velocity. So, this could be density, pressure, temperature, viscosity, whatever. So, this could be anything. So, any physical property. So, that is this what I was sort of pointing out earlier is this, right. Sometimes in some books you will also find it as that, you know, small case d that you are used to, the derivative, that is also written as total or material derivative. But it is important to understand that what I mean by total derivative or material derivative. Okay. So, I think we will stop here. We will start, we will sort of take a little bit of a brief look at this and begin to, you know, introduce what turbulence is all about in the next class. And we shall sort of hopefully I would advise you to look at some basics, very basic fluid mechanics concepts, and it's okay to once in a while, you know, hear some words which absolutely is throwing you off guard. It's totally okay to actually go and consult a reference book, a textbook, and take a look at the, you know, definitions of what this is all about, and it should work. You know, time and again you need to sort of remind yourself. That's also a good way to understand and learn, and not just memorize. I would do that myself. Okay, so I think I'll stop here. So essentially, we discussed, you know, the way of looking at a fluid, which is a Lagrangian view and Eulerian view, and what that basically means in terms of math. You know, how if I were to look at a field in an Eulerian view, then how is the velocity, if I were to ask you, okay, so I am looking at a flow is happening, right, and I am looking at it in Eulerian view, then how is the velocity changing? So, the velocity is changing between one point to the other. So, what we have written here just now, you know, this thing, right. So, this thing is an Eulerian field of view, right. So, how this is going to be useful, and the continuum approach, of course, you have seen how you know, we were looking at things. So, let us see, and let us begin to introduce the turbulence concepts slowly. Okay. So, I will stop here and we will meet again in the next class. Thanks.